Hello, I am John Brennan Peace, and I'll be presenting E2E Tag, an end-to-end trainable method for generating and detecting fiducial markers. In this work, the goal was to train an end-to-end network to both design and detect fiducial markers. Essentially, we are asking the question, if convolutional neural networks are used to detect fiducial markers, what should they look like? To achieve this goal, a three-stage simulation-based approach is proposed. The first stage generates a random fiducial marker using a transposed convolution. The second stage uses a projective transform to warp the marker onto a background image and apply augmentations to simulate real-world capture. The final stage is the detector, which localizes, classifies, and estimates the pose of the marker. The contributions are fourfold. First, a framework for a jointly trained generator and detector. Second, a simulation-based end-to-end training process for randomized back-propagatable superimposition. Third, an analysis on the effectiveness of the synthetic training for real-world deployment. Finally, a methodology for evaluating robust fiducial marker design and detection. Results demonstrate that it significantly outperforms state-of-the-art methods, and it does especially well in challenging image capture scenarios. Now I am going to describe the methodology for generating the fiducial markers. The very first stage is the fiducial marker generator that chooses at random a fiducial marker. We used 30 unique marker classes to conform to comparable state-of-the-art methods, E2ETag and ChromaTag, which both use the 16H5 family. This process is facilitated by a transposed convolution used to map a one-hot vector onto an image. The image on the left is an example of the early stages of training, showing how it went from random noise to distinct recognizable patterns. Since a detector is pre-trained, marker appearance quickly designs an image that best fits the trained convolutional filters. After generating the marker, we warp the marker with a projective transformation. We randomly sample translation, projective warping, rotation, shearing, and scaling parameters in the x and y dimensions and force the projected corners to be within the bounds of the image. To back-propagate the warping operation, we apply the inverse of the transformation matrix to map gradients located within the marker region back to their origins in the marker image. After superimposition, we apply augmentations to simulate the effects of real-world image capture. Motion blur is used to simulate linear camera motion during exposure. The kernel size is set to make sure the tag is not blurred so much that it is indistinguishable from the background. To back-propagate motion blur, the kernel used in the forward pass is reapplied to spread the gradients. Various degrees of contrast are then used to augment the image. This simulates poor exposure and a global scene illumination ranging from bright to dark exposure and from low to high contrast. Then, white balance augmentation is applied. It varies between maximally red, green, and blue. This simulates lighting temperature that varies greatly under shadows, sunlight at different times of the day, and indoor lighting with different temperature bulbs. We augment the image with additive noise to simulate the amplification of the analog signals on the image sensor during capture, and quantization noise introduced by the analog to digital conversion process. Noise is common in challenging capture scenarios such as dark scenes or images captured with a small aperture. To detect the superimposed and augmented marker, DeepLab v3+ with the ResNet 18 is used as it is fast and accurate multi-scale segmentation architecture due to its use of atrispatial pyramid pooling. We removed the decoder from the network as we did not require the upsampling traditionally used in segmentation for our application. The detector reduces the feature vector to size 80 by 80 by 37 and outputs three main predictions for every grid cell. The first channel is the localization prediction, the next 30 channels correspond to classification, and the last 6 correspond to the transformation. Once we superimpose a marker in the image, how does the network know where it is precisely centered? The way we decide to encode that center is by mapping every pixel with a normalized decaying exponential with width equal to 1/2 the marker size and warp the localization target with the marker superimposition transform. The classification prediction is put through a softmax layer and is encoded by categorical cross-entropy. The transformation prediction is encoded with only the origin-centered projective parameters without the translation parameters P3 and P6. For the loss of the localization prediction, we use the mean square error. For the loss of the classification prediction, we use the pixel or grid-wise categorical cross-entropy. For the loss of the transformation prediction, we tried to initially find the loss of the transform prediction directly. However, not all the parameters had an equal effect on the output. Since we were trying to minimize the corner distances between the output and the target marker pose, we used the projective transform produced by the network to warp a set of corners. We then compute the loss as the absolute distance of the corners. The transformation was isolated from the localization by setting the translation parameters to 0. The predicted corners and the target corners are both normalized by the standard deviation of the corner coordinates to penalize the transforms with scale invariance, preventing large markers from dominating training. The strongest detections were chosen to sample the true center. We chose 5 detections, which include the peak and its 4 abutting neighbors. Finally, the aggregate of all the loss predictions with empirically derived scalar multipliers on the classification and localization loss were used for balanced training. We captured at 3024 by 3024 resolution. The corners of the markers were then hand annotated, and both the images and corners were downsampled to 640 by 640 for evaluation. The markers were attached to cardboard squares size 7.62 by 7.62 centimeters. The markers were captured in 7 different scenes. Then 25 images in each scene were captured at uniform distance and angles. We measured the performance of our method versus E2ETag and ChromaTag. We made our analysis a function of the size of the tag to see how we performed versus small tags. For mid-sized tags, it appears E2ETag had a slightly higher recall. However, their precision was much worse. On the other graph, it appears we do a lot better than other methods when tags are presented at a challenging angle. We perform better by a large margin and have nearly a 50% increase in recall and precision. We also measured the performance with a correct code prediction to show our marker is capable of robust identification. There is a large decrease in performance for ChromaTag for both presentations. E2ETag and our method achieve nearly the same performance as the previous methods, with our method decreasing slightly more than E2ETag. We evaluate average precision and recall, as well as average precision and recall with the correct code. Raw indicates real images that have no additional augmentations outside of scene capture. However, images are pristine with possible small degrees of contrast and some white balance. Blur, noise, contrast, and white balance listed in the table are isolated augmentations applied to every image in the test set. Our tag notices much less performance degradation under all augmentations than E2ETag or ChromaTag. The most significant degradation for E2ETag is large blur, additive noise, and heavy green-white balance. ChromaTag appears to be particularly sensitive to noise and low contrast. In fact, it fails on all low contrast images. This is likely due to its detection algorithm not including an adaptive threshold and requires threshold of gradients to be manually set. For end-to-end tag, we experience minimal degradation on all augmentations except for large motion blur. We have better recall under additive noise, dark contrast, and high contrast than the raw images. We assume that the network has favored training under these augmentations, and marker design is made to be particularly robust under these augmentations. The left column images show the localization prediction overlay on the original image shown in red. The green grid cell correlates to the highest value centroid with values shown by the green text box. That grid cell is also the cell used to sample the transformation prediction. The middle column indicates the classification prediction with the 3 most confident class predictions shown by the text box at the top. The blue, magenta, and cyan overlays indicate the values of the most confident class prediction, when that class prediction is the largest for each grid. Although the classification prediction is shown for the entire image, only the grid cells bound by the transform, shown on the rightmost column, are used for choosing the 3 most confident classes shown in the text box. The blue prediction indicates E2ETag's detection. The red prediction indicates ChromaTag's detection. The prediction with red, green, blue, and yellow lines show our detection. The first set of images indicate easier images to detect. The second set of images indicate difficult images with 200% crop. Here are samples of failed detections shown with 400% crop. For the first image, the marker is almost enclosed by 1 grid cell, meaning it is just over 8 pixels wide. All the pixels belonging to the actual tag were in the region for the localization prediction. However, the centroid value did not exceed the threshold for detection, which was 0.5. Here's a sample test video of all 3 tags being detected by their own respective detection algorithms. Notice our tag remains in view under challenging angles and under farther distances. Only E2ETag and our tag are seen until a certain distance is reached, and only our tag is detectable. This is obvious in this image, as our tag is detected first, then E2ETag, then ChromaTag. In conclusion, our method is for generating and detecting fiducial markers with a trainable network. We introduced a simulation-based training framework and demonstrated its effectiveness for real-world image capture. More broadly, this methodology extends to applications that allow for objects to be designed with the purpose of detection with deep learning. Thank you.